2.7 Parent functions and transformations. You know horizontal lines and lines in the form of y equals mx plus b. They belong to families of graphs. Horizontal lines belong to the family of constant functions. The y value remains constant. All lines y equals mx plus b belong to the family which comes from the identity function y equals x. And this is called the identity because the value of x that you put in is the exact same y value that you get. So 5 will be equal to 5. So it's like the identity function 5 is itself. So that is the line that you get. The same points, you will get a 5, 5, you will get a 1, 1, you will get a 0, 0. And that is the identity function. So let's look at some other parent functions which you may not be familiar with. So here's the parent function of the absolute value graph. So y equals absolute value of x. You get a V graph beginning at the origin. And you will notice that it rises up 1, 1 and kind of sort of 1, 1. It's up 1 and to the left on the other side. And this is the absolute value function. The parent function for the, there we go. The parent function for the quadratic, you have y equals x squared, also starting through 0, 0. It would be very important as you get more and more used to how the parabola looks to really take note of these points. It will make your life easier as you graph these parabolas, noticing that to the right and to the left of your vertex, you go over 1 and up 1, you go over 2 and up 4, and you go over 3 and up 9, and that is because this is an x squared. So if you put 1 in for x, 1 squared gives you 1. So that is your 1, 1. If you put in 2 in for x, 2 squared will give you a 4 for your y. So you get a 2, 4, and that is that ordered pair. And those will be the same relationships of those points, even as we move this parabola around the coordinate plane. The same relationships of those points. And you'll see that as we practice these graphs. Absolute value and quadratic functions have a vertex form, just like y equals mx plus b for lines. You should be able to graph the v and the u, the absolute value and the quadratic, by looking at their equations. The absolute value vertex form is f of x equals a times the absolute value of x minus h plus k, meaning that the vertex will be h and k, and we pull h and k straight from here. If you have a subtraction sign, h will be your x value of your vertex, and if there is an addition sign, k will be the y value of your vertex. The quadratic vertex form is f of x equals a times x minus h all squared plus k, and then the vertex will be h and k. As long as you have a subtraction within this set of parentheses, your x value of your vertex will be h, and as long as you have an addition sign with your k, then you have k as your y value of your vertex. As these signs change, the sign on the x and y values will change themselves for the vertex. So let's look at a transformed graph of an absolute value. If we have y, and remember y is f of x, is equal to, and I put in the 1, we're going to look at some not changed as far as the width is concerned, absolute values and quadratics. X minus 3 plus 2, the vertex here is 3, 2. So we have minus and we have a plus 2. So straight in 3 and 2. And so over 3 and up 2, there's our vertex, and we have an absolute value. V graph. Here's a parabola. We have y equals to 1 times, so that is that a from that vertex form, x plus 4 squared minus 2. This squared, you need to understand, is just letting you know you have a parabola. That is letting you know the shape. So you do not square anything in here. It's letting you know, oh, I have a parabola. Let me find my vertex. I have +4, so I have, because it's not a subtraction sign, I have a -4 for my vertex. Because this is -2, I have a -2 for the y value of my vertex. So I begin at -4, -2 for my parabola, and here's those points that I told you about. They have the same relationship to the vertex over 1 and up 1, over 2 and up 4, over 3 and up 9. So it's almost as if you have moved the origin here, but if you look at your vertex, over 1 up 1, over 2 up 4, because we have squared the x value to get these other points. It's almost like you have gone back to that original parent function of the original graph, and you are taking this, just the plane x squared, and you're moving it around and putting in a plane 1, a plane 2, a plane 3 within this x and squaring it, even though now you have this different equation. As long as we have a 1 in front of here. We will practice more of those graphs so this becomes a little more clear. The thing I want you to understand now is this vertex when you're looking at this equation, and get this vertex down and know where do we begin and where do we place this parabola within the coordinate plane. Now, why do those signs change from our vertex form? You should have learned previously in Algebra 1 that in absolute value functions, as in y equals the absolute value of x minus 3 plus 2, to find the vertex, the statement within the absolute value is set equal to 0. So why did the vertex of this equation have 3, 2 as our vertex? Why wasn't it -3, 2? Well, here's why. This statement, to get your vertex for that absolute value equation, you take this statement within the absolute value symbols, set them equal to 0. If I solve this, I get x equals 3. So this vertex was 3, 2, because I set this equal to 0 and I solve for x. What do I get for x? I get a +3. And this is why it seems that the x value are the opposite sign from its sign in the problem. And this is the same with the quadratic x values in the vertex. So it's always kind of a stumbling block for students. Can be a little bit difficult when you look at that vertex form and try to decipher what is my sign. And it is because we set this equal to 0. So as you are looking at this, if I have subtraction, I take this, and it is h. It is not -h, it is h. And as this sign is always straightforward for our y values of our vertex. We like k. K is very straightforward. And that is parent functions and transformations.